Putting this to practice, take a peek at this infinite series. Let's determine whether it converges or diverges. And if it does converge, let's see what it converges to. So take a peek at how I have my first n terms, but it's an infinite series that goes beyond that. But with the definition I just gave you, I think to see if this thing converges, I have to look at the nth term of the sequence of partial sums. And the nth term of the sequence of partial sums is this. Now I'm taking the limit of this. If I get a finite fixed real number, I'm in business. I have conversion for the infinite series. But I can't determine at a glance whether this converges or diverges. But notice how the nth term of the sequence of partial sums is indeed a rational expression. As a matter of fact, the denominator factors quite nicely. Now, committing to partial fraction decomposition, I can split the original fraction into such where a and b are just going to be 2 and -2 respectively. That means I can rewrite the nth term of the sequence of partial sums as follows. A bunch of terms. But let me go to the last term first, because I think I can write that as a 2 over n plus 1 plus a -2 over an n plus 3. How about if I write a subtraction instead of addition? Now here is its predecessor. Here is its predecessor. I missed a lot of terms in between. Let me jump to the first one. The first one was, gosh, what did it look like? This, so 2 over 1 plus 1? Plus a -2 over, is that a 4? The term I generate when I plug 2 in for n is going to be this. When I plug 3 in for n, I get this. How about if I throw in just one more because I have the room? How about the next be 2/5 minus 2/7? And then I have my dot, dot, dot business. All the way down to the last 3 groupings. Now notice something really interesting happens here. Take a peek at how this term right here is the additive opposite of this term. These two are certainly going to be additive opposites. This is going to cancel with one over here that you don't see. Same thing with the -2/7. As a matter of fact, towards the end, notice how this n plus 3 downstairs term does not cancel with anything. But this n plus 1 certainly does. That's positive. That's negative. Matter of fact, the n plus 2 is going to cancel. Actually, not the n plus 2, is it? I meant to say this 2 over n is going to cancel with the second term of this grouping here, which is a -2 over n. Everything cancels at the end except for these 2 terms. So when I take a peek at limiting, as n increases without bound, the nth term of the sequence of partial sums, that's taking the limit as n increases without bound of merely these 4 terms. Is that a 2 over 2 plus 2 over 3? But I also have a plus a negative, oh, there it is, 2 over n plus 2, plus a -2 over n plus 3. But in taking that limit, clearly the second 2 terms completely drop out. They tend to 0. And all I'm really left with, I don't know, is that going to be a 5/3? Since that's the limit of the nth term of the sequence of partial sums, it literally means the infinite number of terms in my infinite series add up to simply a positive 5/3. So yes, indeed, this series does converge. And in particular, it converges to that 5/3. Kind of interesting that with partial fraction decomposition, I got a lot of collapse in these terms. And that happened because I was being very contrived when I made up the example. This isn't going to happen often. But because you see all this collapsing of these terms in this big expansion for the nth term of the sequence of partial sums, I sometimes subclassify the original infinite series as a telescoping series. So whenever you get cancellation like this, hence the title telescoping.